Imagine a person sitting quietly on a park bench. They look completely still, right? But are they really at rest? To the bench beneath them, they are stationary. But relative to the sun, that same person is hurtling through space on a spinning planet at thousands of kilometers per hour. This makes it impossible to define an object's position without first establishing a fixed reference point, or origin. This means that motion is not an inherent property of an object, but a relationship between the object and its surroundings. Every physical description must begin by asking, compared to what? Once we pick that reference point, we find two different ways to measure a journey. Distance tracks the total path taken, a simple scalar value. Displacement, however, is a vector. It measures only the straight line change in position from start to finish. We see this distinction in the practice of pradakshina, where devotees walk a continuous path around a temple. If you walk one full loop and return to your exact starting point, your muscles feel the effort of the distance covered. But because your final position is identical to your starting position, your mathematical displacement is zero. This logic dictates how we measure movement over time. Speed is simply distance over time, while velocity is displacement over time. By adding direction to the calculation, we transition from tracking how far someone has walked to knowing exactly where they stand relative to the origin. In the real world, objects rarely maintain a constant velocity. When they speed up, slow down, or turn, they undergo acceleration, defined as the rate of change of velocity over time. During a snake boat race in Kerala, the boats begin at rest with an initial velocity of zero. The sudden, coordinated effort of the rowers creates an immediate spike in positive acceleration. When those same boats cross the finish line and the rowers dig their oars in to stop, the velocity decreases, an action called retardation. This raises a specific question about the nature of movement. Is it possible to accelerate even if your speed remains perfectly constant? Consider an orbiting satellite. Its speed may be steady, but because its path is a curve, its direction changes at every single point. Since velocity is tied to direction, the velocity is always changing. To a physicist, turning a steering wheel is just as much an act of acceleration as hitting the gas pedal. We decode these changes through data. A position time graph tracks where an object is at every instant. On this graph, the slope of the line provides the object's velocity. A steeper line indicates a higher rate of travel. To track changing speeds, we shift to a velocity time graph, where velocity is plotted against time. Here, the slope represents acceleration. An upward angle shows the object is gaining speed over time. These graphs hold a secondary set of data. By calculating the shaded geometric area beneath the velocity line, we find the object's total displacement. This geometric approach allows us to extract variables like acceleration and distance directly from the shape of the motion itself. Visualizing motion through graphs leads to the ultimate objective, using mathematical models to predict exactly where an object will be in the future. When an object moves in a straight line with constant acceleration, we use these three kinematic equations to solve for unknown variables like time or final velocity. This predictive math has deep roots. In the 14th century Ganita Kaumudi, scholars used similar logic and the ancient unit of the yojana to calculate the meeting times of moving postmen. Today, these same principles dictate modern safety standards. Engineers use initial velocity and retardation rates to define the safe braking distances required on highways. By identifying a few known variables, we can transform chaotic physical movement into a predictable model. You now have the conceptual tools to observe and analyze the physical world. Mastery, however, comes from applying these laws to complex problems. Practice these scenarios at edunudge.in. Our CBSE-aligned question banks and 5-step nudge system provide the guidance needed to solve difficult kinematics problems.